So, welcome to a first segment of an introduction to information theory. In this segment, I will give an overview of information theory, mainly what the area, what information theory is about. And in particular, I will introduce two problems that historically been studied in depth by information theory. So, before I get started, let's first think of what do we mean by information. By the way, I will use the words information and message interchangeably just to avoid overusing the word information. A piece of information or a message basically can be anything. For example, it can be an outcome of an event. For example, what country won the latest World Cup. It can be a number. For example, the number pi. It can be emails. It can be images, videos, and so on. It's actually quite unusual that we have a scientific field that is almost single-handedly established by one person. Claude Shannon has been largely credited as the father of information theory. Almost the entire foundation of information theory is built based on his 1948 seminal paper. Shannon studies two problems. Basically, the first problem is how to quantify amount of information in a message. And in the second problem is how much information it can transmit through a channel. So let's first look at the first problem. It turns out that how to quantify information is very much the same as how much we can compress a message. Because if we think of what is the amount of information in a message, it's really the same as how many bits are needed to represent that message. And if we can use as few bits as possible, of course we want to use as few bits as possible to represent the message in practice just for the sake of compression, and the limit of compression will be exactly the amount of information in that message. However, even given this interpretation, it can be many different ways to interpret it still. For example, in the computer science side, Kolmogorov introduced the Kolmogorov complexity in the sense it thinks of the amount of information as the minimum length of the program needed to generate the information. So it's a rather interesting, I would say even elegant definition. However, it's not very useful because it's really no one knows how to compute the Kolmogorov complexity. So on the engineering side, Shannon instead see the world as stochastic and interpret the minimum amount of bits needed to represent a message using by extending probability theory. And this will result in the so-called Shannon entropy. We'll give more detail of how to compute the Shannon entropy later on in the future segment. But at this moment, let us also look at the second problem briefly. So again, the second problem is how much information we can pass through a channel. It turns out that this problem has a very well-defined solution. Basically, as long as the amount of information is less than a threshold, so-called this threshold, we'll call it the capacity, then we can find a way to send the message losslessly through this channel. On the other hand, if the amount of information of the message is larger than the capacity, then it's impossible to find a way to send the message losslessly through this channel. And we will talk about this capacity thing later on in future segments also. So here I just want to summarize what we did in this overview. So basically we introduced two problems. One is trying to quantify information. It turns out it will be very much related to the compression problem. And the theoretical limit of compression, or the amount of information in a message, will be just the channel entropy. And the practical way to compress a message to the channel entropy, at the rate of channel entropy, is studied in the realm of so-called source coding. And in the second problem is about how much information we can pass through a channel. And it turns out the theoretical limit is given by the so-called capacity. And to achieve the capacity, the practical way is studied. The practical way to achieve the capacity is studied in the realm of channel coding.